everyone. How's it going? So in today's video, we're gonna be solving daily Leetcode challenge, which is soup serving. So we are given a problem. You have two soups, A and B, and it's starting with n millimeter. And in every turn, you're gonna have this four operation that you can choose from. And in the note, it says that there are no operation that pure 0 millimeter from soup A and 100 millimeter from soup B. And the amount of A and B appear simultaneously during the turn. So the goal is to return a probability that A is used up before B plus half of the probability that soup A and B are used up. So the thing is, when the soup A reaches 0 or less than 0, we're gonna return 1 back. And if soup A and B, both of them can goes less than or equal to 0. Like for this one, it's A, and this one can be A and B. If it's less than or equal to 0, then we return 0.5 because they want us to return half of the probability, which is I think it's somewhere right here. Yeah. So also we have to note that in each of the event that happened, we have to multiply it by 0.25 because they mentioned here is independent of the previous term, so we have to multiply them by 0.25. Yeah. So yeah, to get a better understanding of this problem, I think we need to look at some of the example first. So before we look into a more sophisticated example, let's have a look at a simple example where n equal to 50. So we know that based on the problem, we have four operations available. So we represent it as a decision tree where each decision tree represent one operation. So we start here at n equal 50. So we have soup A 50 and soup B 50. So the first operation, we deduct 50 from soup A. Sorry, we deduct 100 millimeter from soup A, which lead us to soup A less than 0. But in this case, I'm just gonna represent it 0 because it's gonna be empty anyway. And we deduct 0 from soup B, so soup B will remain the same. So this is one of the base case that we have reached. So once soup A is empty, what we want to return back is the probability of 1 back to the recursive call. And also in the second operation, we know that this lead to soup A less than 0, but it's still 0 is gonna be empty anyway. So we're just gonna return back a probability of 1 back. And the third operations that where we deduct 50-50 from soup A and B, that will eventually lead us to 0 and 0. This is where we return 0.5 back because remember in the description of the problem, it says that we want to return half of the probability back when A and B are all used up. So we're gonna return 0.5 here back. Um, and in the last operation, we know that we're gonna deduct 75 millimeter from soup B, so it will soup B will end up less than 0, and that means we're gonna return back 0 because we do not need to care when soup B is empty. Yeah, the only three things that we need to care is when soup A is empty or when both of them are all used up. Yeah. So in each operation, remember that each operation is 0.25 probability independent of all of the previous turn. So that means we gonna multiply every base case by 0.25. So when we return this value back, we want to just multiply it by 0.25. Yeah. So in this example, it's just very small example. There's no caching come into play. So in the next example, I'm gonna show you like when there's a we have a bigger n, and then memorization will come into play. Yeah. All right, so let's have a look at another example where n is a little bit bigger. In this example, I will not draw every subtree in for this decision tree. I just want to show you the caching part. So for the left operation, which is the first operation, we know that there's nothing to cache here. At the end, it's just gonna lead to the empty in soup A, and what we want to return back is just here is 1 times 0.25, and here let's have a look at the second operation here. So the second operation will lead us to 125 and 175 for the sub A and B respectively. And if we execute the fourth operation, this is where we execute the fourth operation. So this will give us 100 and 100 for sub A and B. So there's nothing to return here yet, but I want you to look at the fourth operation, which is on the right here. So the fourth operation will give you 175 and 125 as sub A and B respectively. And if you execute the second operation here, you'll see that it will give you the same output, which is 100 and 100 for sub A and B respectively. So as you can see, both of the subtree here and the subtree right here, they they have the same output, which eventually lead to the same outcome. That is why when we compute the output from this decision tree, from this subtree, we don't want to recompute it again. So that is why we apply caching, or another term which is called so-called memorization in for dynamic programming. So yeah, I think that that is pretty much it for the dynamic programming. Um, and yeah, we can continue to the coding part. All right, so let us start our coding. The first thing that I want to do is to create a helper function. I'll call it backtrack. That is what I name it usually for a decision tree. And the parameter will be A and B. That is for represent for sub A and B. And I also have a memo which accounts for caching. Um, yeah, so first condition, we need to check our base case if A is less than 0 and B less than 0. What we want to return here, remember, is half of the probability, which is 0.5. Okay, and the second condition, I might want to check if A is less than or equal to 0. In that case, we want to return 1. And if B is less than or equal to 0, in that case, I'll just return 0 because we don't care. Yeah, right? Um, yeah, so now we get to write our four operations. So the first operation, I'll just call it first operation. That will be a backtrack of A minus 100, and B will remain the same. The second operation would be calling backtrack function, and A will minus 75 and B will minus 25. Our third operation would be backtrack of A minus 50 and B minus 50. Our last operation would be backtrack of A minus 25 and B minus 25. So what we forget here is each of the operation is dependent of previous term, so it has a probability of 0.25 times each of the operation. And I'll just gonna copy that for the other operation. And we can call our caching and give a parameter of A and B, and this will be first operation plus second operation plus third operation and plus fourth operation. And lastly, we just return back our cache, which is the output of it. Also, we need to handle when we find that it's the cache, the A and B already stored in the cache. What we want to do is just return back A and B, the value from A and B. Yep. So now let's just try and run uh, our helper function, and A and B will be N and N. Let's see if that passed the test cases. Okay, some typo. Yeah, so let's run it again. Right, so both of the test cases pass, but there's one more edge cases that we need to handle. So imagine that, let me add when n is very large and maybe it's close to 5,000 and see what happened. What is the value that returned back? So you can see like in the test case 3, n return a value of 1 back, a probability of 1. So we can see the pattern here that when n's grow larger, the probability will get closer to 1. And that means when n is greater or equal to 5,000, we do not want to like compute the value, we just return back a value of 1. If we try to call this function, definitely we will run into time limit exceed. So yeah, that's just only edge cases that you need to handle. Yeah. So let's try submit solution and see if it passed all the test cases. Right. So yeah, it passed all the test cases. It got accepted. Um, yeah. So for this solution, I'll share it in my video description. If you like it, please don't forget to subscribe and give a thumbs up. Yeah, thank you so much for watching, and I'll see you again in the next daily challenge.